On Monday.
Happy birthday.
Thank you.
Okay, so I want to compare two of the matrices we looked at last time. So the title of what we're talking about today is diagonalization. This is section 5.4, I think. No, 5.3? 5.3. Okay, so compare this matrix which I'll call D because it's diagonal, matrix 2, 0, 0, 4. And we saw that this has two eigenvalues. Lambda equals 2 and lambda equals 4. And that the eigenspace for lambda equals 2 was the span, in other words, all multiples of the vector 1, 0. So when you see the span of the vector 1, 0, you should say, oh, well, that's just all multiples of this vector 1, 0. So that has a form, a non-zero number, or whatever, could be up here, but the second component should be 0. And if I take a look at the eigenspace for lambda equals 4, the set of eigenvectors of lambda equals 4, I get the span of 0, 1. So this is all basically in your notes from last time. I want to compare that with the matrix, which I'll call A. We're talking about two of these in the same example now, so I need different names for them. And I think we had the matrix 3, what was it? -1, -1, 3. Is that right?
I think so.
Yeah, I think that's right. And this had eigenvectors lambda equals 2 and lambda equals 4. And the span of the vector, the span of the eigenspace for lambda equals 2, or the eigenspace for lambda equals 2 was the span of, I believe, 1, 1. And the eigenspace for lambda equals 4 is the span of the vector 1, -1. Or was it, did we write negative? I mean, the span of 1, -1 is the same as the span of -1, 1. But I think we wrote it -1, 1. You'll have to check your notes for that, but I think that's how we wrote it. And geometrically speaking, we saw what this first matrix did. This first matrix is a stretch of 2 in this direction, and it's a stretch of 4 that's supposed to say times 2 times 4. So you take vectors and stretch them by a factor of 2 horizontally and stretch them by a factor of 4 vertically. That's basically what this says. That lambda equals 2, that corresponds to the direction 1, 0. 1, 0 is along the horizontal axis. We're stretching things by a factor of 2 horizontally, and we're stretching them by a factor of 4 vertically. And this one did something very similar. This thing stretched things by a factor of 2 in this direction, and it stretched things by a factor of 4 in this direction. So 1, 1 points that way, and -1, 1 points this way. So we're stretching by a factor of 2 that way and by a factor of 4 that way. Everybody with me so far? Awesome. Okay. this is what I want to do. I want to take these two vectors, these two eigenvectors, and I want to make a matrix from them. So let's make a matrix. We're going to make a 2 by 2 matrix using the eigenvectors of A as columns. So the first column, you can do this in whatever order you want. So 1, 1 will be my first column, and minus 1, 1. And I'm going to call this matrix P. I want to make another 2 by 2 matrix. We say make a diagonal 2 by 2 matrix. Using the eigenvalues of A. Want to make a diagonal matrix using the eigenvalues of A in the same order that you used them in P. So whichever eigenvalue this first column goes with, make that the first diagonal entry. So in the same order, you use the vectors. In P. So let me show you what I mean. We have two eigenvalues, 2 and 4. Those are going to be my diagonal elements. Since this first column in P went with lambda equals 2, I'm going to make my first diagonal entry 2. And of course, if this is a diagonal matrix, the off diagonal elements are all 0. And since this was the second eigenvector I used in P, I'm going to use this is my second diagonal entry in this matrix right here. So that'll be a 4. Well, that looks familiar. That's this. I'm going to call this D. D for diagonal. And my question to you is, what do P and D do? We already know what D does geometrically. So geometrically speaking, we already know what D does. It stretches by a factor of 2 along this axis, and it stretches by a factor of 4 along that axis. Geometrically speaking, what does P do? Let's see what P does.
It's a reflection.
It's actually not a reflection.
Oh, really?
Yeah, yeah. I can see why you'd say that. If I had, let's see, what would make this a reflection? If I had a minus sign there too, then I think it's a reflection. But this one's not. You've actually seen this before. Let's see what P does to the vectors 1, 0, and 0, 1. So let's take P times what we sometimes call E1. E1 is the vector 1, 0. So P was 1, negative 1, 1, 1, and E1 is 1, 0. Go ahead and do that multiplication. That should be hopefully easy for you now. You should find it easy to multiply a matrix by a vector. So 1 plus 0, 1 plus 0 is 1, 1. Oops. Do you notice a relationship between between this vector and this matrix? Look at the columns of this matrix. What do you notice about that?
That they match?
Well, yeah, that this is just the first column. It should be clear to you that if I give you any matrix, let me just give you another matrix for a second. How about 1, 2, 3, 4, 5, 6, 7, 8, 9, and go ahead and multiply this by 1, 0, 0. See what you get.
Well, 147.
You get 147, right? 1, 0, 0, 4, 0, 0, 7, 0, 0. So 147. So when I take any matrix and multiply by 1, 0, 0, I'm going to get the first column of the matrix. If I take any matrix and multiply by 0, 1, 0, I'm going to get the second column of the matrix. If I take any matrix and multiply by 0, 0, 1, I'm going to get the third column of the matrix. So of course, I got the first column of the matrix over here without doing any work. What do you get here?
Minus 1, 1.
Yeah, you get minus 1, 1. You get the second column of the matrix. So this matrix P, you've seen this matrix before. And leave those there for now. This matrix P takes the vector takes the vector 1, 0 and moves it to the vector 1, 1. We see a similar matrix anyway. And it takes the vector 0, 1 into a negative 1, 1. It's almost like a rotation, but these vectors are longer. So it's like a rotation plus a stretch. It moves this vector into here, and this vector gets moved over here. Every vector sort of gets rotated counterclockwise 45 degrees and gets stretched a little bit. That's what that matrix does. So if that's what P does, if P takes 1, 0 to 1, 1, and 0, 1 to negative 1, 1. So in other words, takes this vector here and takes this vector here, then P inverse we'll do the opposite. We'll take 1, 1 back to 1, 0. And it will take negative 1, 1 back to, where do we go? 0, 1. Because the inverse always just does the opposite. If that's basically what inverse functions do. They just go backwards. So A takes this vector up here, and it takes this vector over here. A inverse is just going to put this vector back down here. It'll put this vector back up here. Everybody with me so far? Let's go ahead, just take a moment and compute P inverse. You know how to compute inverses. So to get P inverse, we put P down, 1, negative 1, 1, 1, put a vertical bar, 1, 0, 0, 1, and let's row reduce. So I'll row reduce. You don't have to wait for me. I'll take row 2, subtract off row 1. So I get 0, 2, negative 1, 1, I'm going to take the second row and multiply by half. That gives me 0, 1, minus 1 half, 1 half. And then I'll take row 1 and add row 2. So that gives me 1, 0, 1 half, 1 half, negative 1 half, 1 half. In this matrix, since I have the identity over here, this matrix is A inverse, is P inverse. So P is this, P inverse is 1 half, 1 half, negative 1 half, 1 half. Now what we're going to do is the following. Now take P, D, P inverse. P times D times P inverse. Let's ask ourselves, what does this matrix do? So remember, this is a matrix, because if I take a 2 by 2 matrix and multiply by a 2 by 2 matrix, and multiply by a 2 by 2 matrix, I just end up with a 2 by 2 matrix. This is going to be a 2 by 2 matrix. What does it do? So let's take a vector x. So consider a vector x. And we'll see what happens when we do P, D, P inverse of x. So the first thing that gets multiplied by x is P inverse, then D, and then the P last. The P inverse is the closest to the x, then the D, then the P. So let's ask ourselves what each of these things do individually. So let's say we start off with x equals E1 equals a vector 1, 0. So P, D, P inverse of 1, 0. Oh, sorry, not 1, 0. I want, sorry, not 1, 0. I want x to be the vector 1, 1. X is the vector 1, 1. So PDP inverse of 1, 1. What does P inverse do to 1, 1? We said that before.
Change it to 1, 0.
It changes it to 1, 0. So this is P D times 1, 0. So basically, you took this vector 1, 1 and moved it down to 1, 0. Oh, I see. I should put this on a different spot on the board. So I took the vector 1, 1 and moved it down to 1, 0. What does D do to 1, 0?
We'll flip it. So it'll be 0, 1.
No, D. This.
Oh, my bad.
No, it's okay. So, but you want to try again? What does D do to 1, 0?
I'll stretch it by 2 and 4.
Well, which one? 2 or 4?
I think 2.
It
2.
stretches it by 2, right. You can see D stretches 1, 0 by 2, and it stretches 0, 1 by 4. So it stretches this by a factor of 2. So D times 1, 0 is just 2 times 1, 0, which I could just as easily write as 2, 0, but I'm going to write it as 2 times 1, 0. And I'm going to move the 2. I'm going to move the 2 through the P, which I can certainly do because we can always move scalars back and forth through matrices. So 2 times P 1, 0. What does P do to 1, 0?
Change it to 1, 1.
It changes it to 1, 1. So this is going to be 2 times 1, 1. In other words, PDP inverse takes the vector 1, 1 and stretches it by a factor of 2. Now we have 2, 2. Is everybody okay with that? So first, we started off with 1, 1. We went down to 1, 0. That's what P inverse did. Then we stretched it by a factor of 2 and moved it back up here, and it was twice as long as it was before. So it took this original vector and stretched it by a factor of 2. Now take x equals, what was our other one? Negative 1, 1. And let's take PDP inverse of negative 1, 1. What does P inverse do to negative 1, 1? What's P inverse do to negative 1, 1?
Change it to 0, 1.
Changes it to 0, 1. So it moves this vector to here. That vector goes there. And what does D do to 0, 1?
Multiply by 4.
It multiplies it by 4. So this is P times 4, 0, 1, which is, I could just as easily write 0, 4. But I'm going to move the 4 through the P. So 4P times 0, 1. And what does P do to 0, 1?
Change it to minus 1, 1.
It changes it to back to minus 1, 1. So this is 4 times minus 1, 1. So in other words, PDP inverse stretches 1, 1 by a factor of 2, and it stretches minus 1, 1 by a factor of 4. So let me just recopy what we had over here. So we started off with A. A was 3, negative 1, negative 1, 3. We constructed two matrices. B, the diagonal one, which was just 2, 0, 0, 4. We used the eigenvalues of A to build this. We also constructed P, which was 1, negative 1, 1, 1. We used the eigenvectors of A to build this. And we did these two in the same order. Since we used the eigenvalue 2 to make this first entry here, we used the eigenvector that went with 2 to make the first column. Since we used the eigenvalue 4 for our second entry here, we used the eigenvalue for 4 for the second column. If I had switched these two, I would have switched the columns here, and everything still would be okay. Then we wrote PDP inverse, and we saw that PDP inverse did to the vector 1, 1, it stretched it by a factor of 2, which is exactly what A does. So this does exactly what A does to both 1, 1, 1, 1 gets stretched by a factor of 2. That's what A does to 1, 1. And negative 1, 1 gets stretched by a factor of 4. That's what A does to negative 1, 1. We sort of reasoned out how PDP inverse stretches this by a factor of 2. It takes this vector, moves it here, that diagonal stretches that by a factor of 2, and then P puts it back here. So the whole thing was stretched by a factor of 2. This vector gets moved over here, gets stretched by a factor of 4, and then gets moved back over here, and it's now 4 times as long as it was before. I kind of think of this like a rotate, stretch, rotate. So rotate, stretch, rotate back. These aren't really rotations, but that, morally speaking, that's what's going on.
Yeah, and if you actually multiplied PD and P inverse together, you would end up with A.
That's right. I was just about to ask you to do that. That is absolutely right. So go ahead and multiply P times D times P inverse. So
Just multiply them together.
just multiply them together. So P was 1, negative 1, 1, 1. D is 2, 0, 0, 4. P inverse I cleverly erased, but I think it was 1/2, 1/2 minus 1/2, 1/2. Is that right? And as you know, because of matrix multiplication associativity, you can either multiply these two together first and then multiply by that, or multiply these two together first and multiply by that, as long as you don't change the order of the matrices. It doesn't matter which way you group them. Let's go ahead and multiply them together. I'll do these two first, just because I don't know why. So 2 times 1 is 2, plus 0, 0, minus 4, 2, plus 0, 0, 4. And I'm supposed to multiply that by this. 1/2, 1/2, minus 1/2, 1/2. So what we have here is, in the upper left-hand corner, 1/2 times 2 is 1. Minus 4 times minus 1/2 is plus 2. So 1 plus 2 is 3. 2 times 1/2 is 1. Minus 4 times 1/2. So that's 1 minus 2. That's negative 1. 2 times 1/2 is 1 minus 4 times 1/2. So 1 minus 2 is negative 1. 2 times 1/2 is 1 plus 2. That makes 3. That's A. Yeah, that's what we call it, right? Yeah, that's A. So PDP inverse is A, which isn't surprising because it does to the eigenvectors of A exactly what A does. PDP inverse is called the diagonalization of A. And you can read the eigenvalues of A from D. The eigenvalues of A are right here, 2 and 4. Oops. And you can read the eigenvectors out of P. And again, when I look at this, what I think is P is like a rotation. It's not really a rotation, but I think of it as sort of rotation-like. I rotate one of my eigenvectors onto one of my axes. D stretches along an axis, or possibly reflects if it's negative. And then I rotate back to where it was in the first place. And so my eigenvalue is stretched. My eigenvector is stretched. That's what PDP inverse does. It does what A does in 3 steps, where each step is kind of obvious. D is just a stretch along the axes, and P inverse are like rotations. They're not really rotations, but they're kind of like rotations. It's not hard to come up with a diagonalization. It's built out of stuff you already know how to do. You take A, find the eigenvalues, write them as the diagonal entries of a matrix. If you do that, you already got D. Find the eigenvalues, the eigenvectors. In your first column, put whatever eigenvector went with whatever you put right there. In your second column, whatever eigenvector you get that goes with that eigenvalue, put it right there. If you have a third column, whatever eigenvalue went there, put the eigenvector which goes with it right there. It's not difficult to do. And then to get P inverse, find the inverse. Admittedly, finding the inverse is sometimes a little bit of work, but for a 2x2, it's not that bad. How do you feel about this? This okay? Not hard to find a diagonalization of a matrix. Now, I have to tell you some unfortunate facts of life. Not all square matrices can be diagonalized. For various reasons. I'm not going to go into what they all are now. For example, the matrix, let's see, what do we have? The matrix 0, 1, -1, 0, which is a 90-degree rotation, can't be diagonalized because it has no eigenvalues. We saw that this has no real eigenvalues. So we're not going to even be able to write down D. You can't diagonalize it. No eigenvalues, no eigenvectors. Here's another matrix that has perfectly nice eigenvalues, but you still can't diagonalize it. This can't be diagonalized for different reasons. If you want to play around with it, I will let you play around with it and see what goes wrong. But I'm not going to, it's a little bit beyond the scope of the course. This can't be diagonalized either. For different reasons. You have eigenvalues, but you don't have enough eigenvectors. I'll just write that down. Not enough eigenvectors. And again, if you want to play around with that, you'll see what goes wrong when you try to find the eigenvectors. If we were going to be able to find, the diagonalization for this, we'd need two linearly independent eigenvectors for our two columns. And there's no way we're going to be able to do that. Not for that matrix. So diagonalization, not hard. I hope you sort of review that idea where basically what P does is kind of rotate, and then D sort of stretches or compresses or possibly reflects, depending on what those diagonal entries are, and then you know, P rotates back. So P inverse, then stretch or compression, then P rotates back, and that's how I think about it in my mind. Let's see, how are we doing? 5 minutes. There's only one more idea from this chapter I want to talk about, but I think I'm going to start that on Monday. So I will see some of you in 15 minutes, and some of you I will see on Monday. Hope you all have a wonderful weekend, and I am going to post one more homework for this class. We have, if you're keeping an eye on the calendar, we will have one more midterm, which is scheduled for a week from today. And because you guys have been so diligent about, you know, staying with me and keeping up, I've been able to sort of get to the point in the curriculum where I think we can spend the entire last week reviewing, doing problems, practicing, so that you feel completely ready for your exam. We'll have lots of chances to sort of ask questions and make sure that you feel comfortable doing any kind of question that I could possibly put on the exam. How's that sound? Okay. Okay. So I will see you all when I said I would see you, 15 minutes from now, or 14 minutes from now, or Monday. Have a good one, everyone.
You said our midterm is next week?
Next Friday. Well, like not Friday during class, but I'll post it on Friday, and you'll have like the weekend to do it.
I got 2 more tests like that.
2 more?
Yeah, I got Dr. Sheldon's and Dr. Wan's in the same day as well.
In that case, remind me again on Monday, and I will make a scheduling thing so that you don't have them all crowded together.
Okay, I appreciate that.
Yeah, no, Jalen, no problem. I'm not trying to make your life difficult, I promise. I'm trying to make it easy. I'm really working hard to make your life easier this semester, considering what we're going through.
Yeah, because Dr. Wan and Dr. Sheldon made their tests on the same day.
Then just remind me on Monday, and we will work out the scheduling.
Okay, thank you. I appreciate that.
Of course.